what is stationary wave in the first place? Now, you will learn two types of waves in your syllabus. The first one is progressive wave. The second one is stationary waves. Progressive wave, you learned in the previous chapter that it was wave where the wave profile moves and energy is transferred from one point to another. Stationary wave is the direct opposite of progressive wave. Stationary waves are just waves where the wave profile does not move and energy is not transferred from one point to another. Okay, now stationary waves are actually produced by progressive waves. They are produced when two progressive waves of the same type and equal frequency overlap when traveling in opposite directions at the same speed. Okay, same type here means it must be light and light wave, it must be sound and sound wave, or if it's microwave, it must be with microwave. If it's infrared, it must be with infrared. That was what we mean. It cannot be like sound and light together form a stationary wave. Okay, so they must be of the same type, they must be same frequency, and they must be traveling in opposite directions so that they overlap. Only then will you get your stationary wave. Okay, now the progressive waves that actually form the stationary wave will not be seen. Okay, but the resultant stationary wave that appears can be seen clearly, and it appears to be standing still. All right, so what we'll tell you is that on the stationary wave, there will be points at which the amplitude of vibration is always zero. Those are called nodes. There will also be points at which the amplitude of vibration is always maximum. Those are called antinodes. Okay, and then after that, we'll tell you that distance between adjacent nodes. Let me clear off everything. Distance between adjacent nodes or adjacent antinodes will be equal to half a wavelength. All right. So this is something like a free shot of a stationary wave. Okay, where it normally looks like this. Okay, it normally looks like this. The point where it normally doesn't vibrate is this, are these points here. Those are your nodes. You notice they will never vibrate. But there will also be some other points on the stationary wave where it vibrates, and it vibrates with maximum amplitude. Those will be these points here. Okay, these are what you will see. And then what we'll tell you is that distance between adjacent nodes will be equals to half a wavelength. Okay, adjacent node is this one and this one, right? So distance between adjacent node is half a wavelength. Similarly, we can also say to you that distance between adjacent antinode is going to be half a wavelength. Here is adjacent antinode, right? Okay, so this is something like a common diagram that is used to illustrate to you what is a stationary wave. I will play a video later for you to understand better what is a stationary wave, but let me just go through some of this stuff here first. Okay, now there is also a very common question where they will ask you, what are the main differences between progressive wave and stationary wave? The first few points, this one should be readily understood. As I mentioned to you, progressive wave profile moves from one point to another. Energy is transferred from one point to another. But when you go to stationary wave, it's the direct opposite. Wave profile does not move from one point to another, and then energy is not transferred from one point to another. This part can be readily understood. It's the next two parts that sometimes need a bit of explanation. Okay, now for progressive wave, we will also tell you that the amplitude is constant for all the particles. And then adjacent particles are not oscillating in phase with each other. If you look at stationary wave, we'll tell you that for stationary wave, amplitude varies from a minimum or zero to maximum. And then particles between adjacent nodes are always oscillating in phase with one another with a phase difference of zero, whereas particles in adjacent loops or opposite sides of a node are always out of phase with one another because they have a phase difference of 180 degrees. All right. Okay, so let me just show you an animation to illustrate to you what we mean. Okay. Just give me a few seconds to open up the video. We go with progressive waves first. It's raining over here, so I hope you can get me over the rain. Okay, we are repeat. Okay, now this one is the progressive animation for progressive wave. So that time when I first taught you wave, I told you guys that this is what you call your wave profile. Okay, say this one is at the wave profile when t is equals to 0. You will see that later on as I let the wave run, this same wave profile will start to move. At some instant of time, it may look like this. This is where t is equals to 1. And then another instant of time, it could look like this. This is where t is equals to 2. Right, so let me just show you that and play the video. Okay, so notice that that wave profile is actually moving from one end to another. Okay, so because the wave profile is moving from one end to another, it's also transferring energy along with it. The wave profile contains energy, right? Since the wave profile is moving from one end to another, it's also moving energy from one end to another. That explains the 2 points earlier that you saw in the table. Okay, if you look at the third point in the table for progressive waves, we mentioned that the amplitude of the waves, the amplitude of the progressive waves are constant, right? So what it means by that is that, again, let me just freeze the diagram. Say for example, now I freeze the diagram. Before the wave passed through, let's assume that all the particles were in equilibrium. Okay, let's assume that before the wave even passed through, all the waves were in equilibrium. Okay, but then when the wave has started to pass through, at this time, say maybe at some random time t here, all these individual particles A, B, C, D, E, F, G, H would displace according to the wave profile, right? Okay, so what you understood is that A will oscillate up and down, B will also oscillate up and down, C will also oscillate up and down, D will also oscillate up and down. Okay, it applies for all the particles as the wave profile moves. But what I want you to see is how the amplitude of the particle is as the wave profile changes. See, now I play the video again. You notice that all the particles, it will oscillate up and down. But then when it comes to the amplitude, you notice that they all seem to have the same amplitude. You see, they don't exceed this line here. And they never exceed the lines that I've drawn here. All the particles, they will oscillate up and down as the wave profile travels. But you notice that the amplitude, which is the maximum displacement from equilibrium, for all the particles are the same. Okay, this is what we mean by constant amplitude for progressive waves. Okay, this is what we mean by constant amplitude for progressive waves. All right, so far so good with this. Okay, then another part here in the table was that we told you that adjacent particles are not oscillating in phase with each other, right? Okay, so what we can say here is something like this. Say for example, right now, let me just erase all the. Okay, maybe I make use of another different set of points. Maybe I look at these points here. Okay, so say I look at these points here. Maybe I make it bigger. Right? 1, 2, 3, 4, 5. Okay, so let's name this particle again X, Y, Z, A. I have right now alphabets. Okay, I'll just label them 1, 2, 3, 4, 5. Okay, so let's just say right now at this particular wave profile, use this color. At this instant of time, again, this one is say maybe t equals to 1 second. I notice that at this time, t equals to 1 second, particles 1, 2, 3, 4 have all displaced according to this positions here. All right. Particle 1 here, particle 2 here, particle 3, particle 4, particle 5. All right. Now, I know that my amplitude position is here. This is my amplitude position. Now, notice that when these particles are being displaced, particle 1 maybe is at 0.4 of the amplitude position, and then of its amplitude, and then particle 2 is maybe at 0.8 of amplitude, and then particle 3 is amplitude itself, and then the same goes with the rest here, which is symmetrical. So here you see they seem to be moving up, but then they are not. How should I say this? In terms of the position right now, okay, with respect to fraction of a cycle, this one is at 0.4 of its amplitude. This one is at 0.8 of its amplitude. Okay, they are not in phase. This is what we mean by not in phase. When we say that the particles are oscillating in phase, it means that they're all exactly at their amplitude position. If particle 1 is at amplitude, particle 2 and 3 must also be at amplitude. If particle 1 is at 0.5 amplitude, particle 2 and 3 must also be at half, if particle 1 is at half the amplitude, particle 2 and 3 must also be at half amplitude. If particle 1 is at 0 amplitude, particle 2 and 3 must also be the same. Okay, this also applies to 4 and 5, all right? For all the particles here, when we say that they oscillate in phase, maybe I say this now. If the particles are to oscillate in phase, they must be in the same fraction of their cycle. Okay, this one seems a bit, right? If the particles are to oscillate in phase, they must be in the same fraction, same phase of the cycle. Okay, not same fraction. They must be in the same phase of the cycle, right? So basically what I just mentioned was that if any one of these particles is in amplitude, all of them must be amplitude. If any one of this particle is in half the amplitude position, all the particles must also be in half the amplitude position. If one of the particles is at say 0.2 of the amplitude position, all the particles must also be at 0.2 at the amplitude position. But from what you can see here, that they are not at the same phase of the oscillation. So this one cannot be considered as oscillating in phase. All right. Looking at this, it's a bit hard to see why. You have to see it from the stationary wave part. Okay. So this one is talking about the progressive wave. We now move on to the stationary wave. Okay. Wait. Hopefully it will become easier to see after this. Wait. Let me see where's the stationary wave. Give me a second. Okay, for stationary wave, it looks like, open up. Okay, wait. Okay, now you should be able to see a new video now. Okay, should be able to see a new. Should be able to see. You should be able to see the animation now. Wait, let me ask you guys one thing. Just now when I played the animation for progressive wave, can you see the animation? for the progressive wave. Did I share it properly with you guys? Oh, okay, great. Okay, so now you can see the stationary wave, all right? So I was afraid that maybe I did not share it properly. Okay, so now you can see the stationary wave here. This is an animation of the stationary wave. Now, if you recall back to the beginning part of the notes, all right, to the beginning part of the current page that you're looking at, I mentioned to you that stationary waves are formed by two progressive waves that are moving in opposite directions with same frequency, and they overlap to produce your stationary wave. Okay, so then after that, we mentioned that stationary waves have wave profiles that do not move, and energy is not transferred from one point to another. So from what you can see now on your screen, you should be able to see three different types of waves: a green colored wave, a light blue wave, and a yellow colored wave. Okay, so of interest to you is the yellow colored wave. Okay, the yellow colored wave is the stationary wave. I want to use the annotation tool, but I cannot use it. Wait, now let me just open up. I'm having trouble using the annotation tool. Okay, now I can use the annotation tool. Okay, right. So of interest to you is the yellow color wave. The yellow color wave is your stationary wave. Okay, let me just freeze the video a little. This yellow colored wave that you see here is your stationary wave. Okay, your wave profile is this. Okay, this one is your wave profile. Right, this one is your wave profile. Okay, now I want you to look at that wave profile. You notice that the wave profile isn't actually moving from one end to another end. It's very different from the progressive wave that you just saw. The wave profile actually moved from one end to another end. But this one, you see the wave profile wasn't actually moving from one end to another end like this. Instead, what it seemed to be doing was that it's just going up and down. All right. So this is what we mean by wave profile not moving. Okay, the moving part is the part where we didn't see it moving from this end to this end. Okay, stationary waves do not have wave profiles that move. The wave profile won't be moving from one end to another. It's just there oscillating up and down only. Okay, so that is one key point of stationary wave. And then because your wave profile wasn't moving from one end to another end, you don't transfer energy also. Okay, so this is stationary wave. And then how is this stationary wave formed? It's actually formed by two progressive waves moving in opposite directions that overlap with the same frequency and speed. Now, the blue colored wave that you see going towards the left and the green colored wave that you see going towards the right, these are your two progressive waves which actually form the stationary wave. Okay, the blue color progressive wave is moving towards the left. Okay, let me just try and see this. Okay, your blue colored wave, this one, this is the wave profile of the blue colored wave. And then after that, you have the green colored wave, which is this one. Okay, this is your wave profile. Okay, notice that the blue will move towards the left, the green will move towards the right. These two are your progressive waves because your wave profile moves, but they're moving in opposite direction. Okay, so just look at it carefully. Green moves to the right, blue moves to the left. The wave profile is moving, they are progressive waves, and they're both moving in opposite direction. And then as they're moving in opposite direction, they're continuously overlapping. Okay, So because they are moving in opposite direction and they're continuously overlapping, it causes a new wave to be produced according to principle of superposition. That new wave that you see being produced is actually your yellow colored wave that you see here. Okay, this yellow color wave, as I mentioned to you, is your stationary wave. Okay, the wave profile does not move and no energy is transferred from one point to another. It just oscillates up and down like that. Okay, right? So then after that, there were some things that were of interest to you also for the stationary wave. This one, let me just continue playing it. Okay, one of the first thing that was mentioned for the stationary wave, under the third row of the table for stationary wave, it was mentioned that the amplitude of stationary wave is not constant, right? The amplitude varies from a 0 to a maximum. So let's look at it this way. Let me just freeze the stationary wave at almost equilibrium. Okay, so let's consider again the case of the particles right now along this stationary wave. Say this one is the stationary waves particle. Okay, particles A, B, C, D, E, F, G, H, and I. Okay, so notice I just want you to focus on this set. All right, A, B, C, D, and E. Okay, just focus on A, B, C, D, and E. Now you have played the video, look at how the particles oscillate up and down. All right, so just look at it a bit more. Look at how the particles oscillate up and down. Okay, now you see this one now is where they are at almost equilibrium position. Okay, now if I let time run, all the particles will start to move up and then it will eventually reach a maximum. Okay, so let me just let it go to the maximum one last time. Okay, this is the maximum that each of the particles A, B, C, D, E, and move will move. You see, A by right actually did not really move. B move up here, C move up here, D move up here. E also considered to be somewhat not moving. So now you see, if I look at these three particles that have displaced, this one is already at amplitude, maximum displacement from equilibrium. This one is also already at amplitude, maximum displacement from equilibrium. This one is also at amplitude, maximum displacement from equilibrium. But notice that the magnitudes are not the same. Just now when you were looking at the progressive wave, remember I drew a line across like this, and then I told you that the amplitude of the progressive wave would always reach that line. The amplitude of all the particles along the progressive wave will always reach that line, representing the amplitude. So I say that the amplitude was constant there because all particles will reach that line that has the same amplitude value. But now you look at this one for your stationary wave, as the particles oscillate, they actually will reach their maximum displacement, they will reach their amplitude, but it will not be the same value for all the particles. Okay, different particles will have different values of amplitude. So if you look at particles B, C, and D, you notice that they never reach the same amplitude. They all have their own respective amplitudes. And then when you look at their respective amplitude values, they're not going to be same. You see, this value here is not the same as this value here. So I can say that they don't have same amplitudes. Okay, that's why you also notice that particles A here and E here, they actually did not vibrate. The part amplitude here was actually 0. Whereas in the progressive wave, none of the particles have a case where they don't vibrate. They all will vibrate to a maximum, to an amplitude position. And then the amplitude is the same throughout. But for your stationary wave right now, you notice a curious case where some particles don't vibrate, the amplitude is 0. And for the particles that do vibrate, the amplitude is not the same. That's why you will notice on the third row of your stationary wave column of the table, we say that the amplitude varies from 0 to a maximum. Okay, that is what we meant by that. Progressive wave, the amplitude was constant. Okay, that one was for progressive wave. Okay, but this one, amplitude varies. Okay, let me write this properly for you. This one, amplitude varies for stationary waves. Okay, right, so the amplitude varies. This one we understood. So far, so good. Okay, so the amplitude varies. The part where the amplitude is 0, this one will be your node. Okay, so the definition in the page that you're looking at, we mentioned that node is the point where the amplitude of vibration is always 0. So you see these particles here, A and E, if I let the animation run, you will notice that they never vibrate. This is where the amplitude of vibration, this is the node. Okay, because this point is where the amplitude always remains 0. Okay, and then after that, you look at the next statement. After that, they say the antinode is the point where the amplitude is maximum. Okay, so the amplitude is not constant. The amplitude varies from 0 to a maximum. So you look at your stationary wave right now, which one seems to have an amplitude much higher than all the other particles? It will be this one, isn't it? Particle C. You notice that whenever it reaches amplitude position, it is much higher than all the other particles. Particles B will never reach as high as C. Particle D will never reach as high as C also. Okay, so this part here is where you have maximum amplitude. This one is your node, antinode. Okay, antinode is the point where your amplitude is maximum. Okay, for the rest of the particles, particle B and particle D, they have the amplitude positions, but it's not maximum. There is some other particle with a amplitude higher than it. Okay, they don't have the maximum amplitude here. The maximum amplitude belongs to the one in the center, particle C here. Okay, so that's what we meant by antinode and nodes now. All right, so far so good. Okay, then after that, I move on to the other part where we mentioned to you that the particles in between adjacent nodes will always vibrate in phase. Okay, this one I will have to make use of some other particles here. Okay, maybe I make use of this region here. Particles, okay, I make use of this one here. All right. A, B, C, D, E, F, G, H, I, J, K, L. Okay, maybe I add another one just to H, I, J, K. Okay, now let me just try and make it bigger. J, K, L. Okay, so let's just say right now I want to focus on these particles here. H, I, J, K, L. All right, H, I, J, K, L. Okay. Now, the other part in the table mentioned that particles between adjacent nodes will always vibrate in phase, right? So let's just say right now, this region here, particle H and particle L, is my node. Okay. So think of it this way, you see that H don't seem to vibrate, L don't seem to vibrate, isn't it? Maybe this one I needed to draw it a bit towards this side. You know, just bear with me for a while. Okay, H is here. Okay, H is here, right? Here is node now. Okay, this is the best I can do right now with this one. Okay, so just look at this one, HIJKL. All right, let's assume that H is my node, L is my node. Okay, because they are right over here. The particles don't vibrate up and down. These are my nodes. And then after that, I have IJK, where J is my empty node. Because this one I can see is clearly going to give me my empty node here, right? And this is empty node. All right. So now, when you look at this one, maybe I should include more particles. You know, H, I, J, K, L, M, N. Okay lah. Maybe I do it this way. Okay. Particle H and N are nodes. Particle K is my empty node. All right. So right now, at this particular position of my stationary wave, I just want you to focus on IJKLM. All right. Don't need to focus on H or N because those two I mentioned to you are your nodes. Okay, these two are your nodes. So don't need to focus on those two. I just need you to focus on IJKLM. All right. Now, look at how the stationary wave is moving for IJKLM. Now, if I freeze the video, notice that right now, if K is at equilibrium, I, J, L, and M are also at equilibrium. This one, you notice that the amplitude is 0. Okay. Then after that, I let the video run again. Okay, now, this time, I, J, K, L, and M are now displaced according to these positions. All right. Right. So they are all at their amplitude position now. Okay, this one here, right now, they are all at amplitude. Okay, each of these particles, I, J, K, L, and M are at amplitude. The amplitude values will be different, no doubt, but the thing is that they are all in the same phase of the oscillation. Particle I is at the amplitude, J is at the amplitude, K is at the amplitude, L is at the amplitude, and so is M. Okay, that's what I meant by the same phase of their respective oscillation. The other day, if I let it run again, okay, now the new wave for stationary wave is here, right? Notice that now K is here, L is here, M is here, J is here, I is here. Now, with respect to their own oscillation, okay, with respect to their own oscillation for each of the particle, you notice that this one, all the particles are at half the amplitude position. Okay. Again, the values would be different, but they are at, with respect to their oscillation in terms of the phase, they're actually half the amplitude position. The other day, I will let it run a bit more. Maybe now, okay, you know, let me see some of the position. Okay, here. Okay, now I freeze it again. This is now the new position of the wave. All right. This is now the new position of the wave. Is there any other color I can use? Green maybe. Now particles I, J, K, L, and M are over here. They're now at say 3/4 of the amplitude positions. So same thing again. For each of the particles, they are at that same phase of the oscillation. Now they are all at 3/4 of the amplitude position. The amplitude position itself no doubt will vary from particle to particle, but in terms of the phase in their oscillation, in terms of the fraction in the oscillation right now, they're actually all the same. Okay, so this is what we mean by particles between adjacent nodes having particles between adjacent nodes oscillating in phase. If you look at the stationary wave part under the table of the nodes, it was mentioned that particles between adjacent nodes will always oscillate in phase, right? When we say oscillate in phase, it means they're actually in the same phase of the oscillation. If one of them is at the amplitude, all of them will be at the amplitude. If one of them is at equilibrium, all of them will be at equilibrium. If one of them is at amplitude, all of them will be at amplitude. And then if one of them is at half the amplitude position, all of them will be at half amplitude. If one of them is at 3/4 of the amplitude, all of them will be at 3/4 of the amplitude position. That is what we meant. Particles between adjacent nodes will always oscillate in phase. Okay, so far so good with that. Okay, then another thing that I will need to mention to you is that particles on either side of a node, particles on either side of a node or on adjacent loops will always oscillate out of phase. That one is more like this one. Okay. How would I see this? Okay, now this one I would have to look at this one. Okay. Okay, so now let's just say right now I look at this particular node. Okay, just look at this particular node. Okay, look at this node. And this is the node that I want to consider. All right. So now I just need you to look at this entire line of particles, right? You look at these particles E, F, G, H, and X here, okay? And then you look at here, particles I, J, K, L, and M, J, K, L, M, N, right? Now at this position here, you notice that I, J, K, L, M, they're all at amplitude. But then when you look at particles E, F, G, X on the other side of the node right now, they're also at amplitude. But you see they're negative amplitude. All right. And then if let's say right now, I let them go to half the amplitude position. Particles I, J, K, L, and M, they're now at half the amplitude. But so is particles F, G, and X. They're also at half amplitude, but negative half, right? So needless to say, if I let it run to maybe 3/4 amplitude for this one will also be at 3/4 amplitude, but negative. If this one I let it run to 1/4 of the amplitude position, this one will also be at 1/4 of the amplitude position, but negative, all right? So they're having exactly the same displacement, just that it's in opposite direction. Okay, this is what we call oscillating out of phase. If you read the notes, they say that particles on either side of your node, which means either side of this is the node I consider, particles on either side of the node, you notice they're oscillating out of phase. If this one was going up, this one will go down. Similarly, if this one go down, this one will go up. and they all have exactly the same displacement. Okay, that is what we mean oscillating out of phase for particles on either side of a node or for particles on adjacent loops, right? So what do we mean by adjacent loop? You can see from here, if I let the video run, this one here forms one loop. This one here also forms one loop. This is what we mean by adjacent loops, okay? When it comes to the stationary wave, particles on adjacent loops will always oscillate out of phase, always same displacement, the opposite direction. Sorry, not to say same displacement, sorry, that's the wrong term to use. The idea is if they are amplitude, all of them are amplitude. If they are half amplitude, all of them are at half amplitude. If they are quarter amplitude, they're all at a quarter amplitude. All right. They are like in the same phase of their oscillation or same fraction of their oscillation, so to speak. Just now I used the wrong term. They're not having same displacement. The values are different for all the particles. But in terms of the fraction of their oscillation or phase of the oscillation, they are the same. Just that it's opposite direction. Okay, so this is for stationary wave. Okay, then the last thing I just want to talk to you about is why do we say that nodes and antinodes, the distance between adjacent nodes and antinodes are equal to half a wavelength? The reasoning is because of this. You see, if I try to freeze the diagram properly now, like this. Okay, wait on, let me just try and do it again. Wait on. Okay, now this one is me freezing the diagram already. Now you notice that for the progressive wave, this is not a good color to use. You notice that for the progressive wave, this one is going to be wavelength, okay, for the progressive wave itself. But then just now it was mentioned that these portions here that don't oscillate is your node. Okay, it was mentioned that distance between adjacent nodes will be half a wavelength. So you see from here, for one complete wavelength, you have these three nodes here. If you just look at distance between adjacent nodes, it's actually going to be half a wavelength. That's why we told you that distance between adjacent nodes will always be half a wavelength. Okay. And likewise, it's the same now. If I told you distance between adjacent antinodes, this one actually being antinodes here, distance between adjacent antinode will also be half a wavelength. Okay, so that's why we say it as that, right? Okay, so that is stationary wave. Oh wait, sorry, I suddenly stopped the thing. Okay, so this is what we mean by stationary wave. Okay, it becomes easier if you can visualize it. All right, so that is okay. All right, so stationary wave part is done. There's still some small part here, but this one I'll have to leave it for next week. Okay, so stationary wave, there are some things that probably we can do. Let me just see what questions are there. Maybe just one question. I don't have a question here that I can do. Okay, now we just do something simple. Just have a look at page 6. All right, maybe we just do the first part, then after that. Okay, oh wait, it's 6:15. Right, just have a look at page 6. I'll just roughly brief you through this so that you can do this before I end the lesson. June 15 P22. Okay, page 6 of your worksheet. You just do this as homework later, all right? Okay, so state two differences between progressive wave and stationary wave. Yeah, this kind of question does come up quite often. All right, they will want you to explain what are the differences between a progressive wave and stationary wave. So the answers will be any one of those things that I just mentioned inside the table of your note. Progressive waves transfer energy, but stationary waves do not. Amplitude is constant for progressive waves, but varies from maximum to minimum for stationary waves. Or you can also say the ones in red, adjacent particles are in phase for stationary waves, but out of phase for progressive waves. Okay, this one is the bit, yeah, adjacent particles are in phase for stationary waves. This is actually the same as you saying particles between adjacent nodes are in phase, right? The nodes there mention particles between adjacent nodes are in phase, right? That one is actually a better term to use. The marking scheme, you put it as adjacent particles are in phase. It's actually more accurate to say particles between adjacent nodes are always in phase, rather than saying this. This is not as detailed, okay? And then for progressive waves, you will always just say that adjacent particles are out of phase, all right? Now you have a source S of microwaves that is placed in front of a metal reflector R as shown in this figure. A microwave detector D is placed between R and S. So R is here, S is here, okay? So they are asking you, describe how stationary waves would be formed between I and S. How are stationary waves going to be formed between those 2 points? So from what was described here, you have a source of microwave. The microwave source is emitting microwaves towards the reflector. Okay, so this one is your incident wave, incident microwave. It is heading towards the reflector. So once the microwave hits the reflector, it gets reflected back. So you're gonna have a reflected microwave. Okay. Now, since this reflected wave is actually from this incident wave, usually we will tell you that they have the same speed as well as frequency because they're essentially the same wave. All right. So from what you learn under the concept of stationary wave, we mentioned to you that stationary waves are formed when two progressive waves of the same frequency and same speed travel in opposite directions overlap. Okay. Generally, you just join in. We are under page 6 of the worksheet. All right. We're under question B, part 1. All right. Okay. Yeah. So stationary waves, as I mentioned, they are normally formed when you have two progressive waves traveling in opposite directions with the same speed and frequency. Once they overlap, you're going to get your stationary wave. That is the basis of formation of stationary wave. So right now the question is asking you, how are the stationary waves formed between I and S? All right. Now, be very careful about the questions that you see sometimes. Whether are they asking you in general how stationary waves are formed, or whether are they asking you how stationary waves are formed specific to the diagram given in the question. Like your case right now, they're asking you how stationary waves are formed specific to the diagram given in the experiment. So your explanations needs to relate to the items inside your diagram. If let's just say they were just asking you for a general case where they just ask you describe how stationary waves are formed without referencing to any diagram or whatsoever, usually you will just use this definition for formation of stationary waves, which is under page 18. Okay, if they're just asking you for a general definition of how stationary waves are formed, you could just write this. Okay, but in your case, this one is asking you formation of stationary waves specific to a particular diagram. So your explanation must relate to that. That's why you notice that your answers have some specific mention to the diagram. For example, they tell you that microwaves from source S is reflected at reflector R. You must have these 2 words. The reflected and further incident waves will superpose, overlap, or meet each other. Since the waves have the same frequency and speed, stationary waves are formed. Okay. Now the term frequency, you can always replace it with some other thing like wavelength, or period. Okay, speed must always be inside. Right, usually you need to mention two items only, is speed or frequency or wavelength or period. Just choose either one of these. But usually it's better just to say frequency, standardize it. All right. Okay, so this is formation of stationary waves between R and S, described with respect to your diagram. Then the next thing they'll ask you is how D is used to show that stationary waves are formed between R and S. Okay, so let's just say, for example, if you have formation of stationary waves between those 2 points, it could look like this. All right, it could look something like this. Just bear with me for a while. Okay, it can look something like this. Okay, it shows you something like a snapshot of the stationary wave that is formed. Okay, last week we went through the animation that shows you how a stationary wave is. You remember that the wave just goes up and down. Okay, it just goes up and down, but it never goes towards the left, neither does it go towards the right. Okay, so that was your stationary waves. Now, there were some specific points of interest on your stationary waves, namely nodes and antinodes. So the point where you don't have any amplitude or vibration, those are considered to be your nodes. Those are the points where your amplitude is always 0. And there will always be some specific points where your amplitude of vibration is maximum. The amplitude at that point is always the largest. So this one here is antinode. Okay, so they're asking you how D will be used to show stationary waves are formed between R and S. In principle, you know stationary waves are formed between R and S, but how would you detect it? So that's the reason why you have your microwave detector here. Okay, now your microwave detector here detects the microwave. All right, now so if your node is where you have 0 amplitude, you expect to detect 0 intensity of microwave. Whereas for your antinode, that's the point where you have maximum amplitude. You're gonna detect maximum intensity of your microwave. So you imagine right now, if you were to move your detector towards the left and towards the right, you will keep on hitting the nodes and antinodes alternatively. Okay. Once you hit the node, you will hit the antinode, and then you will hit the node again, and then you will hit the antinode again. So from your detector, you ought to be detecting something like max intensity and 0 intensity alternating with each other. Okay, so you see that you have maximum intensity and 0 intensity or minimum intensity alternating with each other. That will tell you that you have stationary waves formed because you are hitting the nodes and antinodes. All right, so you will say that when detector D is moved between source S and the reflector, you will detect maximum and minimum readings on the meter. Okay, so only these 2 points are given mark. Okay, they need you to mention what you do with the detector. You move it between source N and reflector R, and what you expect to see. Maximum and minimum readings. Okay, so maximum is where you have your antinode. Minimum or 0 readings is where you have your node. Okay, so the last statement here, maximum reading is the position of antinode, minimum reading is the position of node. That one is actually not required to be stated inside the question. It's something like further explanation. Okay, right, so that one is okay. Then I move to the last part of your question. Now, describe how wavelength of the microwaves may be determined using the apparatus. Okay, so they want you to describe how would you use this apparatus right now to determine the wavelength. Okay. So if this one is okay, then we just go back up to the same diagram. Okay, so if you recall what I mentioned in the notes before, it was mentioned that distance between adjacent nodes or adjacent antinodes will always be equals to half a wavelength. So looking at it from this little diagram that you have here, distance between adjacent node would be half a wavelength. So here to here, this is not right. This one will be half a wavelength. Or between antinode and antinode, this is also half a wavelength. Okay. So if you know that distance between adjacent antinodes now, say for example, is equals to half a wavelength, the distance between adjacent antinodes could also be thought of as distance between adjacent max readings. Okay, so you try to rearrange this, you're gonna get lambda is 2 times of distance between adjacent max readings or mean readings if you would. Okay, depends on what you want. Okay, so your answer would be something like this. Measure the distance between either adjacent maxima or minima. The wavelength is twice the distance between the adjacent minima, maxima nodes or antinodes. Okay. What I wrote here kind of includes everything. You really only just need to write one. What I mean by that is that if you just write measure the distance between adjacent minima, that one would be sufficient. You don't need to talk about maxima. Or you say measure distance between adjacent maxima, that one is sufficient. You don't need to mention minima. You don't need to mention all the case. Just pick one. Either is adjacent minima, either is adjacent maxima. Minima is the plural form of minimum. Maxima is the plural form of maximum. So minima is the plural form of minimum. Maxima is the plural form of maximum. Okay, so I'll just choose either one. So that's where your 2 marks come from. All right. Then with it, if let's say I say measure the distance between adjacent maxima, the wavelength is twice the distance between adjacent maxima. So keyword here is make sure you mention the word measure. Make sure you mention the word adjacent. That is important to be written. Okay. So that one is okay. So this one should be fine, right? Okay, so the next one that we can do while you're copying the answer is page 1, question 26, or question 28, I think, sorry. Page 1, question 28. You can have a look at page 1, question 28, right? Okay, so if that one is fine, then we look at page 1, question 28. All right, so page 1, question 28. Okay, sorry, I'm looking at the notes. Right, so I'll clear off everything here. Now, the diagram shows you a stationary wave on the string at 2 instants of maximum vertical displacement. The frequency of the wave is 12 Hertz. What's the speed of the wave? So whenever you want to do your questions, please make sure whether you are dealing with a stationary wave. Okay, for the topic of superposition, how you will treat it depends on whether you were able to identify what was the situation there. if before this previously you see that the question is mentioning double slit or something like two source interference, you know that you will always use one equation. If you notice that they're talking about diffraction grating, you will use another different set of equation. Like for now, this one, when you see mention of stationary wave, it is neither of the two cases. It is neither talking about double slit, it's neither talking about diffraction grating, it's talking about something entirely different. All right. So this is a diagram of your stationary wave. Find out the speed of the wave. Speed of the wave is v equals to f lambda. You know frequency. You're just missing the wavelength. So from here, you can actually see this. These points here is actually your nodes, because you see they don't seem to vibrate. Okay, and distance between adjacent antinodes, distance between adjacent nodes as I mentioned to you is equals to half a wavelength, right? So since this one is going to be half a wavelength, you have three of them right now. This one is going to be 3 half wavelengths. Okay, so if it's 3 half wavelength, that would mean that 3 half wavelengths is equals to 90 centimeter. So 90 times 2 is 180 divided by 3. Lambda is 60 centimeter. Okay, so lambda is 60 centimeter. From here, subsequently, you use V equals to F lambda. Frequency is 12 hertz multiplied with your wavelength of 60 centimeter change to meter is 0.6 meter. You get 7.2 meter per second. Okay, so answer is B. Right, so this is one simple application of it. Okay, then we move on to question 2. Okay, sorry, not question 2. We move on to page 2. Okay, question 27. All right. So the next one is page 2, question 27. We'll go through that one now. Right, so let me just clear off this drawing here. And move on to page 2, which is this one. Okay, now page 2, question 27, this one. This is kind of like that question that you've just done for the structured question. So source S emits microwaves with constant amplitude. The microwaves hit the metal screen P and are reflected. A stationary wave is formed between S and P. The wavelength of the microwaves is much smaller than the distance between S and P. A detector Q is moved at a slow constant speed from S to P. What happens to the amplitude of the signal detected by Q? So you read this one. This one is like that question that you just did on page 6. This one here. All right. So what's happening here is that you have microwaves going towards this direction, and then microwaves being reflected in the opposite direction. So waves in opposite directions overlapping with same speed, same frequency, you're gonna have stationary waves. So your stationary wave would look something like this. Okay. So you have your nodes. And then you have your antinodes. Okay. So where you have nodes, you're gonna have minimum reading. Where you have antinodes, you're gonna have maximum reading. Okay. You have a detector Q right now, right? They're telling you that your detector is actually moving at a constant speed from S to P. Mean to say it's moving like this. Okay. So over the time that it's moving, it will hit the node, it will hit the antinodes. So you're gonna have mean reading and maximum reading alternating with each other. So in the context of this question, what's the amplitude of the signal detected by Q? Your detector here, you can say that you notice that the amplitude will increase and decrease regularly. Regularly here kind of means that it is alternating with each other. First you see increase, then you see decrease, then you see increase, and then decrease, and it repeats itself over and over again. Okay, so increase and decrease steadily, simply because of this. Right, so I can say that from P, sorry, from S to P, the detector passes through node and antinode regularly. So thus your answer is this. From S to P, the detector will pass through your node and antinode regularly, thus your amplitude increase and decrease regularly. Okay, so this one is for that. Okay, next one, page 12, question 30. Right, page 12, question 30. Okay, have a look at page 12, question 30. Right, so I'll just clear off everything here. Now, to produce a stationary wave, okay, to produce a stationary wave, two waves must travel in opposite directions through the same space. Okay, stationary wave. This one is talking about stationary wave right now. What statement about the properties of the two waves must also be true? Okay. So one of the main things was that there must be same speed. Another thing must be that they must have same frequency or period or wavelength. Okay, another one is also this. There must be same type of wave. It cannot be, say, light wave and sound wave, because one of them is transverse, one of them is longitudinal. And even when you're talking about about transverse wave, if let's say you have microwave versus radio waves, these two cannot combine together to become a stationary wave. No doubt that these two are transverse waves, but you cannot combine together to give you a stationary wave. It must be microwave and microwave, must be radio wave and radio wave. Okay, that's what we mean by same type of wave. If it's microwave, it must be all microwaves. If it's radio waves, all must be radio waves. Okay, so your answer here is easily going to be C. All right. The moment you see here different speed, wrong, different speed, wrong, different wavelength and frequency, this one wrong. Okay, everything must be same. Okay, so answer is C. Right, so that one done. Then we go to page 14. All right, so have a look at page 14. I believe this is a structured question. Right, so let's have a look at page 14. Okay. Okay, this one is something else. Okay, have a look at page 14. Okay, have a look at page 14. Now, November 15, P21. This one, question 5. Question 5. All right, now, a progressive wave transfers energy. A stationary wave does not transfer energy. This one we know already. State two other differences between a progressive wave and a stationary wave. Okay, so this one again relates back to what I just explained extensively last week. For progressive wave, amplitude is the same for all particles in a progressive wave. Okay. Whereas for stationary waves, amplitude varies from maximum to a minimum or zero for stationary waves. Okay, this is for the first one. And then the second one, you could say that adjacent particles are not in phase for progressive waves. Okay, so this one not in phase, whereas wave particles are in phase between adjacent nodes for stationary waves. Okay, this one is in phase. Okay, basically it's just reproducing what you saw in the notes. Okay, so as long as you understand this one should be okay. So if you don't have time to finish writing it, you can do it later by copying it from the notes. All right, then I go on to something that is more worthwhile. Okay, now look at part B. A stationary wave is formed on a stretched string between 2 points A and B. The variation of the displacement y of the particles of the string with distance x along the string for the wave at time t equals to 0 is as shown. Okay. Now the wave has a period of 20 milliseconds and a period of 1.2 meter. The maximum amplitude of the particles of the string is 5 millimeters. Sorry. On figure 5.1, draw a line to represent the position of the string at t equals to 5 milliseconds, and then state the phase difference between the particles of the string at x equals to 0.4 meter and at x equals to 0.8 meter. Okay, so this one, if you are looking at your worksheet right now, you're probably only seeing this straight line here. This one here is when t is equals to 0. Okay. So this is what you're seeing right now in your existing worksheet. The question is asking you to plot the graph for that same string with a stationary wave at t equals to 5 milliseconds, which is actually going to be this one. Okay. Is it 5 milliseconds? Yeah, 5 milliseconds. So how do you kind of do this? Notice that the question already mentioned the frequency for you. Sorry, they did not just mention frequency, they actually mentioned period. The question specifically told you the period of 20 milliseconds and wavelength of 1.2 meter. Okay. Now, when you see this one here, the wave has a period. This means that each particle oscillates with a period of 20 milliseconds. Okay, to better illustrate what I mean by that, I think I should probably refer back to the animation. Just give me a few seconds to open it up for you. Okay, video, standing waves, this one. Okay, let me share the video with you right now. Okay, now you should be able to see the video. All right. Okay, so back to that same animation that I was showing you last week. Okay, the yellow colored wave is your stationary wave. Okay, so right now, let me just freeze the diagram properly at the right timing. Okay, you can imagine that stationary wave as this stationary wave that's being shown in your video right now as the stationary wave that is being displayed by the string inside your question. All right, so if I consider that there were a few particles along the length of the string, one particle here like this. Okay, I'm just going to draw some random particles. So A, B, C, D, E, F, and G. Now this one would be the case where your stationary wave is at t equals to 0. Okay, so just now the question mentioned that your period is 5 milliseconds, meaning to say each of the particle oscillates, sorry, not 5 milliseconds, my mistake. Your particle has a period of 20 milliseconds. Okay, my mistake. Your period is 20 milliseconds. So I mentioned to you each particle will oscillate with a period of 20 milliseconds. That will mean that for the particles A, B, C, D, E, F, G that you see here, they will oscillate up and down with a period of 50 seconds. Wait, let me just freeze it properly. Okay, your particles A, B, C, D, E, F, G, H, and I will all oscillate with a period of 20 milliseconds for all particles. Okay, so particle A will oscillate up and down with 20 milliseconds. Particle B will oscillate up and down with 20 milliseconds. Particle C also oscillate with a period of 20 milliseconds. But bear in mind that the amplitude of their oscillations will not be the same. Okay, this is the first thing you learned under stationary wave last week. I mentioned to you specifically that amplitude of oscillation of the particles in a stationary wave will never ever be the same. Okay, there will be one point where amplitude is always 0. There will be one point where the amplitude is always maximum. And then in between, you have something in between 0 and maximum. Okay. That being said, all the particles here, although they have different amplitudes, they all have the same period. Okay. So this one here, if the question mentioned to you, they have an amplitude of 20 milliseconds, sorry, a period of 20 milliseconds, all will have a period of 20 milliseconds. Okay, so let's go with this one. If let's say I give a convenient point for you to look at, let's just look at particle C. Okay, just look at particle C, the one that is right in the middle, that is probably your antinode. Okay, just look at particle C here. All right, so let's say right now at t equals to 0, the particle is here. If this particle C wants to complete one oscillation, it will have to go up. Maybe I erase this. Okay, it will have to. Which color is good to use? Blue color. It will have to go up, and then go down, and then go back up again. Okay. Basically, it has to go out like this, going down, and then go back up again like this to become one complete oscillation, thereby your t being 20 milliseconds here. Okay, so if I look at particle C alone, for it to complete one oscillation, it will go up and then down and then go back up again in order to complete one oscillation. So this one takes 20 milliseconds. Now notice that in the time that it took to do that, your motion can actually be divided into 4 equal portions. This one is your first, going like this. This one is your second, going like this. This one is your third, going like this. And then this one is your fourth, going like this. So if you take 20 milliseconds divided by 4 different stages, each of these will be 5 milliseconds. Okay. Right. So this is for particle C. The same analysis can also be applied to particle D here or E here. Okay. You will get that same kind of motion. You have 4 distinct phases, so 4 distinct sequence. Each sequence is 4 distinct parts now. All right. 4 distinct parts for the oscillation. Each part takes 5 milliseconds. So that altogether you get a complete oscillation and a period of 20 milliseconds. Okay, so if the question says that they want you to plot the graph for the stationary wave at t equals to 5 milliseconds, it will actually just be this one. You know, this one is at t equals to 0. This one I froze the picture at t equals to 0. So if t equals to 5 milliseconds, it will go like this. Okay. T equals to 5 milliseconds, this will go up to this point. So everything else will kind of follow that same pattern. Okay. So that's why you notice that the shape of your graph is like that. And also they also mentioned one thing. The question mentioned that your wavelength is 1.2. Okay, the question mentioned that your wavelength is 1.2 meter. So wavelength of 1.2 meter would be this one. And this one is 1.2 meter, the wavelength. Okay. So that's why you will draw this shape in your answer right now. Okay. So I'm just going to change the screen again. Whatever I just wrote here will disappear once I change to the PDF view. Okay, you can refer to this in the recorded lesson later. Okay, so let me just go back to the diagram. Okay, so that's why you get this shape. All right, that's why you get this shape. All right, where your wavelength is 1.2 meter. Oh yeah, and another thing also that I think I didn't really mention is this. They mentioned to you that your maximum amplitude of the particles of the string is 5 millimeter. This one actually kind of refers to the amplitude at antinode. Okay, because you know that for all the particles, maximum only occurs at antinode. Okay, so when you draw that shape out just now, 5 milliseconds, the maximum possible one will be 5 millimeter. Okay, so just draw it accordingly, where your wavelength is 1.2 and your maximum, which corresponds to your antinode, is 5 millimeter. Okay, and this one will give you 3 marks, just like that. Okay, so this one is for this. Okay, then after that, if you have drawn this one here, you move on to the next part of your question. Okay, now the question is asking you right now to state the phase difference between particles of the string at x equals to 0.4 meter and 0.8 meter. 0.4 and 0.8. Okay, so let's go with that. Okay, so when you have drawn your graph just now, where we tell you that you need to have a wavelength of 1.2 meter and a maximum amplitude at antinode of 5 millimeter. The question is asking you to find out the phase difference between particles at 0.4 meter and 0.8 meter. Okay, now based on what you have here, this one is roughly in the middle. This one is 0.5, I think. Okay, so where would 0.8 be? This is 0.5, 0.1, 0.2, 0.3, 0.4. 0.4 would be somewhere around here. Okay, I'm just drawing it from what I can see here. I could be wrong. You can see your diagram better. 0.4 is here, and then 0.8 would be, this one is 0.6, 0.7, 0.8. Okay, 0.8 will be here. Okay, this one is 0.8. Okay, so your particles at 0.4 and 0.8, what is the phase difference between those two particles? Okay, now when you get questions like this, when you want to find the phase difference, you don't apply that same method that you learn in waves, okay? Stationary waves is a bit different, right? I know that in the waves chapter previously, phase difference, you have a certain method to find, right? Where you're trying to find fraction of a cycle, right? For stationary waves, specifically for stationary waves, don't use that same method, okay? This one, without doing what you learn in waves, you can just see that here is your antinode. Sorry, here is your node. This big point here is your node. Okay, this one is your node. Remember what I mentioned about the phase differences between particles, for particles between adjacent nodes and for particles on either side of a node? If you refer back to your notes under page 18, remember this? I say particles between adjacent nodes will always be in phase. If one of them is at equilibrium, all of them will be equilibrium. If one of them is at amplitude, all of them will be at amplitude. If one of them is at half amplitude, everything will be at half amplitude. This is for particles between adjacent nodes. Now, for particles in adjacent loops or opposite sides of a node, they will always be out of phase, having a phase difference of 180 degrees, meaning to say they will always have the same, they will always be having the same displacement, but opposite, okay? The displacement will always be same magnitude, but opposite direction, okay? If one of them is at amplitude, the other will be at negative amplitude. If one of them is at half amplitude, the other will be at negative half amplitude. So maybe it's better for me to show you the video again, this one, okay? So say for example, I tell you that this one was the node that I indicated inside your question. This is the particle at 0.4 meter. And then this is the particle at 0.8 meter. So notice that these particles are always moving opposite directions. This one moves up, this one moves down. Or if this one moves down, or if this one moves down, this one will move up. Okay, so they will always be 180 degrees out of phase. This one you don't really need to do any calculation. You just need to remember the fact, since they are on either side of a node or opposite sides of a node, they will always be having a phase difference of 180 degrees. Okay, so no calculation required. So this is 180 degrees or pi radian, depending on what you want. Okay, so this one is for part 2. Okay, now for part 3, state and explain the change in kinetic energy of a particle at an antinode between 0 and 5 meters per second. Numerical values are not required. Okay. State for us the change in Ke of a particle at the antinode between 0 and 5. You don't need to say any, you don't need to do any calculation, you don't need to show any values. Okay. All right, so this one will kind of relate to what you learn in waves. All right, let me just show you that diagram again. Okay, one of the things I mentioned to you in waves was this. I told you that for any particle that's oscillating, speed is 0 at amplitude position. This was one thing I mentioned. And then I further mentioned that speed is maximum at equilibrium position. Okay, so recall this from the waves section I mentioned to you before. Speed 0 at amplitude. Speed max at equilibrium. Okay, so just now the question say to you, just look at the antinode position at 0 and 5 milliseconds. So if say right now I single out your antinode for you, let me just single out the antinode for you. Say your antinode is this one here, and this one is your antinode at, okay, this is your antinode. So at t equals to 0, this one, your antinode being here, it should at equilibrium position, because you're at t equals to 0, your particle is at equilibrium, right? So at t equals to 0, you are at equilibrium. Max speed, therefore Ke is max. Okay, so this is at t equals to 0. Then just now from the analysis in part 1, you know that at 5 milliseconds, it will go all the way up to the maximum possible displacement, right? At t equals to 0, it will go all the way up here. And this one is the new position at t equals to 5 milliseconds. So this one is already at amplitude. Okay, so this one is at amplitude. So 0 speed. Therefore, Ke is 0. Okay, so the question is asking you to look at the motion of the antinode at 0 to 5. Okay, so if you're looking at it in that particular direction like this, Ke is max here, Ke is 0 here. The conclusion you should be getting is that Ke is decreasing. Okay, Ke here is decreasing. So let's go back to this one. All right. So you should get something like this. Yeah, your conclusion is that your Ke is decreasing. All right. So you can just say that t equals to 0, particle has kinetic energy because the particle is moving. They didn't really say maximum kinetic energy here. At t equals to 5 milliseconds, the particle has no kinetic energy as the particle is stationary. Thus, there is a decrease in kinetic energy between 0 and 5 milliseconds. Okay, so that is the understanding here for this particular question. All right. Okay, so this one should be okay. Then let me just have a look at the others. Maybe we can just do one more MCQ before I move on to the next part of your question. Okay, so this one I hope is okay. All right, the next one that I can probably have a look at for you is page 20, question 24. Okay, so let's have a look at page 20, question 24. Page 20, question 24. All right. Okay, now question 24 under page 20, which is this one. Now the diagram represents the pattern of stationary waves formed by the superposition of sound waves from a loudspeaker and the reflection from a metal sheet, which is not shown. So right now they're asking you, W, X, Y, Z are 4 points on the line through the center of the waves. Which statement about these stationary waves is correct? Okay. So let's just look at part D. Okay, maybe we just look at the answer choice A, B, C, D first. All right, maybe we do it in order. Okay, now an antinode is formed at the surface of the metal sheet. Say for example, you have a metal sheet here. This is your metal sheet that is being shown here right now for your understanding. They're saying that an antinode is formed at the surface of the metal. We need to say you're getting something like this. This one is what we call as antinode. Okay, because at the surface here, you have this, right? If let's just say you have a node at the surface of the metal, it actually looks like, it will actually look like this. This one if it's a node lah, you will get this, something like this. Okay. This one here, in terms of looking at the pattern, this one will be your node. Okay. Now, this one here actually is supposed to be covered in the next lesson, in the next thing that I'm going to teach for stationary waves, but I just mentioned it to you first. When they say that an antinode is formed at the surface of the metal sheet, this one is wrong. This is definitely wrong. Okay. I will just mention this to you first. You will get an understanding of it later. At any physical barrier, it will always be a node. Okay. At any physical barrier, it will always be a node. This one is something I will explain later. Okay. So here when they say to you an antinode is formed at the surface of the metal, this one by right is wrong because metal sheet is a physical barrier. If you are forming a stationary wave, it should always be a node. Okay, this would be the correct one. This is wrong. Okay, so answer A is incorrect. You want to choose the correct answer. Okay, then after that, the next statement. A node is a quarter of a wavelength from an adjacent antinode. Okay, so a node is a quarter of a wavelength from an adjacent antinode. Basically, it could mean something like this. If this one here is a node, and this one here is also a node, and the middle is your antinode, distance between adjacent nodes, as I mentioned to you before, will be half a wavelength. So the question is asking you between node and an adjacent antinode. A node is a quarter of a wavelength from an adjacent antinode. Basically, they're asking you about this. From this antinode to this node, how much do you think it is? So if node to node is half a wavelength, node to antinode is half of whatever you have here. So half times half wavelength would give you quarter wavelength. Okay. So this one here will be quarter wavelength. Okay. So this one is correct. A node is a quarter of wavelength from an adjacent antinode. Okay. So far so good. All right. Okay, then we look at C. The oscillations at X are in phase with those at Y. Okay, so you're looking at particles X and particles Y. And notice that this one here again is your node. So remember I told you before, particles in adjacent loops, particles on either side of a node or adjacent loops always oscillate out of phase. This one they're saying in phase. So this one again is out. All right. Then last one, look at this one. The air particles oscillate perpendicular to line WZ. Line WZ is this one here. WZ is this one. There's the horizontal line there. They're saying that the particles are oscillating perpendicular to line WZ. Now, look at what kind of wave is this. This one is sound wave. Okay, so sound wave is longitudinal. So oscillation is parallel to WZ. The question says perpendicular, meaning to say they expect the air particles to oscillate up and down perpendicular to your wave travel. Okay, let's just say that this is the direction of your wave. Okay, your particles, they're saying they're oscillating perpendicular to it. This one is wrong. Okay, because it's sound wave. If it's sound wave, it will always oscillate parallel to your direction of wave travel, or in other words, parallel to your WZ. Okay, so this one again is wrong. So correct answer is D. Okay.